Okay, so the next set of materials can be about reactions. Uh, and hopefully you've taken a look at the first four videos. Really give you a basic idea what single why we balance equations, uh, a simple kind of combustion reaction in dealing with alkanes. And we'll talk more about that. I'll get back in combustion after this set of material. Then we talked about single replacement and double replacement, and those videos really are for you to get a background of what's going on. Uh, the next two PowerPoints are going to be really what your class 121 is going to have to do. It's going to be more in depth than 110, which they just basically take single replacement reactions, take the word equations, and change it to a chemical equation, and then balance it, and then tell what's being oxidized and reduced. Uh, what we want to do now is we want to go more in depth into that, and this is what you're going to be really responsible for. Okay, so this next test, and you'll see this is going to be really it's going to be single replacement and double replacement reactions, and doing all of the stuff that we're going to do over the next two PowerPoints here. So the first one here is called single replacement expanded. Okay, so this is going to expand what explaining, I talked in depth what happens with single replacements on the previous videos, but this will be what you have to be able to do. So in the first video of single replacement, what you saw was is that basically you're given a word reactance. The words for the reactants, like calcium sulfate plus aluminum, and then what you would have to do is tell me what the product would be. In that case, it would be aluminum sulfate plus copper. Okay, so you just swap, and then what you had to do is change the names. So that I had to change the names to the formulas. Okay, so copper sulfate be CuSO4, and aluminum would just be Al. Okay, no charge on it. Remember that. Okay, and then when it switches over, the aluminum gets the charge Al3 plus, and so forth. Okay, and we'll go in depth. But now what we want to do is extend on that. Okay, and so first of all, not all the single replacements take place. We're going to talk about that. Also, when we write the equations, we didn't do this when the previous video, is that we have to include the states of the substances. And then we're going to write down, we're going to look at what happens in this chemical reaction, because this chemical reaction takes place in water. So what we want to do is write an equation to represent what the species of the chemicals look like when they're in water. And then what we're going to do is look at, from the ionic equation, we'll be able to tell what substances will react in the chemical reaction, and then we'll be able to write the net ionic. And then finally, we'll really get into understanding what has been oxidized and reduced, and we'll actually be able to tell to show how many electrons have moved from one metal to another. Okay, so let's get into it. So predicting if a reaction works using the activity series. So there's something called an activity series of metals. Easy find. You can find it in books, or you can find it on the internet. And there's different arrangements of them. Actually, I have one here that I'll use. There's other ones that are actually upside down compared to one I use, but we'll leave it at that. Okay, so just taking any metal and putting it in it with an ionic compound that's dissolved in water isn't always going to cause a chemical reaction. Okay, so just because you have a metal and throw it in with an ionic compound, it doesn't mean it's going to happen. What has to happen is the metal you add, okay, it has to have the ability to get oxidized better than the metal in the ionic compound. So the metal that you add, and we'll see the examples of this in the near future here. This is like, well, even in the previous video, you saw when you put a penny copper and it was silver nitrate, what happened is that reaction took place. And why that was is because copper had a higher ability to lose electrons than silver. And actually silver had a better ability of grabbing hold of electrons than copper. So there always has to be one guy that has a higher ability to lose electrons, and the other metal has to have the opposite ability to gain electrons. So how are we going to determine this? Okay, and this is where we're going to use the activity series. Okay, so the activity series, this one here I have below, it's from empirical data, but actually it's pretty close to theoretical data too. We could talk about that when we get into atomic structure. And what it says is the atoms at the top, these guys up here, have a higher ability to be oxidized, okay? Okay, so these guys up here oxidize or lose electrons really easy. So lithium, okay? Lithium is the best metal at losing electrons empirically, okay? While gold, on the other hand, is least likely to lose electrons, and that's one reason why gold is so expensive and rare and stuff like that, because it doesn't rust, it doesn't get oxidized, okay? And it can last for just a really long time. So when they find it on ancient substance, like mummies and things like that, it hasn't oxidized because it has a really low, in fact, almost nothing can oxidize gold. All right, it can be, but it takes a lot of power to really oxidize it. So, so these guys down here are high reducers, so they have a tendency really to gain electrons. Okay, so what you want to do is combine one of these guys down here and one of these guys up here. Okay, so what we're going to see is, and that's what we're going to see in our single replacement reactions. All right, so let's do a couple. So let's say I take copper and put solid copper metal, like a penny, and you put it in an aqueous silver nitrate. Okay, so we talked about that in the first video, is you have to dissolve the silver nitrate. And will this reaction take place? So for this reaction to take place, the lone metal, copper, has to be higher on the table. Okay, so if it's higher on the table than silver, so if this one's lower on the table, then this reaction takes place. Okay, so so if you come over here, you'll see there's copper and silver, and copper's higher on the table than silver, so this reaction will take place. All right, now let's say I put some solid copper, a piece of copper, into some sodium chloride that's been dissolved in water. Will that reaction take place? So this guy here has to be higher on the table and then sodium. Okay, so here's copper, and where's sodium? Sodium's up here. Okay, so this reaction will not take place, okay, because sodium is higher up on the table. All right, so that's the first thing you got to do. You always got to make sure that the reaction takes place. All right, next thing you do after you determine the reaction takes place, what you're going to do is write the equation, starting out with the word equation, and make sure you have all the states. So in the example we used with copper, we'd write the equation, the word equation. Kind of got sloppy on the first video I just said copper plus silver nitrate. But you say solid copper metal is added, okay, to aqueous silver nitrate, yielding solid silver metal and aqueous copper 2 nitrate. Now, how do you know it's 2 versus 1? what we're going to assume is if you're not told, you pick the metal that the oxidation, the highest oxidation state. So if it's copper 1 or copper 2, pick copper 2. If you have iron, iron could be iron 2 or iron 3. Usually pick iron 3 unless you're told it differently. So the way to write that in the chemical equation is you have the S stands for solid, AQ stands for aqueous. Aqueous means dissolved in water. And solid, aqueous. Also, don't forget, you got to please put down all the charges because this is going to be important here, okay? This 0 means is that silver has no charge when it's a solid. Same thing with copper. When it's a solid, it has no charge. But notice over here, when it becomes aqueous, it gets a charge, and we'll talk about that. All right. All right, the third thing you want to do is write down what happens. You want to write the chemical equation showing what happens when you put it in water. So when you put the copper in the water, it stays solid. Okay, nothing happens to it right off the bat. Okay, it's like it's like you're not even adding these two together. Just what happens to these guys when you put them in water. So when you put copper in the water, nothing happens. It stays copper. Now when you put silver nitrate in the water, what happens is the two silver nitrates split apart. Okay, so you have Ag plus NO3 minus. Okay, and what happens to it is when you put this in water, it splits apart. Okay, and it does that twice because you have two of them. If you go back and look at the balanced equation, so we have another one. And so you would have two Ags and two NO3s. Okay, so this is what it would look like in water. Now on the other side of the equation, the silver stays as silver, but the copper nitrate, the CuNO3 gets split. So when this gets put in the water, okay, it's CuNO3, two of them, and then when you put them in water, they all split apart. Okay, put the charges on. Okay, so now you have one copper and two nitrates. Okay. So this sometimes is the hardest part to do, okay, when you do these, is that the ionic compounds split apart. The 3 doesn't split off of the nitrate because the nitrate stays together as a substance. Okay, so what do you have when you put the two together? Here's your reactants, which is right here. And then here's your products, which are right here. And this is called the ionic equation. So it shows you what all the species look like when they're in water. Okay. This is before and after. Okay. All right. So what I want to do is I want to go over some of the splitting apart of the ionic compounds. Okay. I'm just going to go. So let's say you have in the equation you have 1 MgCl2. Okay, so you could write it out like this. Okay, and when you put it in water, what happens is it splits like this. So you have 1 Mg, you don't have to put the 1, and 2 Cls. Okay, so if the equation said plus 1 Mg, 2 plus Cl minus 2, then the ionic equation would look like this. All right, now let's say you had calcium phosphate. Okay, again, let's just put a coefficient of 1 here. And what does it look like? It looks like this. So you could rewrite this whole thing as this, 3 calciums and 2 phosphate. And you put it in water, they all split apart. Okay, so you end up with 3 calciums and 2 phosphates. Okay, all right, now let's take a look at this one. Now let's say in the chemical equation you have 3 aluminum carbonates. What is that going to look like when you write it out in terms of an ionic equation? Well, so let's just piece it. Okay, so we're going to just look at 1 aluminum carbonate. So 1 aluminum carbonate would look like this. Okay, and you have 3 of them. Okay, and when you put them together, when you put them in water, everything splits apart. Okay, and I left the minus off of this too, but okay. So then you count them all up. You got 1, 2, 3, 4, 5, 6 aluminums. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbonates. Okay. Now, some of you might just go, "Oh, well, I don't need to do all this drawing out to figure this out." You think you can go directly from here to here, and you might be able to do that. But if you want to make sure, and I mean, if I was working in a lab and I had to come up and I had to do this, and I wanted to check my answer, I would actually do this step. I wouldn't assume that I could figure it out just by going from here to here. So I don't mind doing this step at all, okay? Because this way I can keep track of things. Right, let's do a couple more examples. Okay, so here's a couple more. So let's say you had 2 sodium oxides. Each sodium oxide looks like this. Okay, when you add up the total number of sodiums, you have 1, 2, 3, 4, and 2 oxygens. Okay. Let's say I had 6 sulfuric acids. Okay, each sulfuric acid is going to look like this. And so you have so 1, 2, and you do that 6 times, you have 12, and then you have sulfates 1, 2, 6. Okay, now in the future you'll see things like this. 4H2 no charge. Don't split that apart. Okay, so don't split this into 8 HOs. Okay, the other common mistake is this right here. Students will write, instead of writing 12 H pluses, they'll write 6 H2 plus. Okay, and that's wrong. Remember, the reason why this 2 here is because you have an H plus and you need 2 of them for every 2 minus. So H plus, H plus, H plus, H plus. So for every sulfate, you need 2 H pluses. That's why the 2 is there. The reason why this 2 here is just that's the way hydrogen is when it's an element, found in elemental form. And we'll see this when we talk about the acids. All right, next thing is write a net ionic equation. And this is where we will see actually what happens. So what you're going to do is, if you look at the previous reaction, you'll notice is that you have 2 nitrates on both sides. They cancel out because they don't participate in the reaction. They just stay the same. So since nothing happens to them, just cancel them out. And then you end up with this here. Okay, so the net ionic equation is simply these ionic equation without the spectator. Okay. All right, next thing is we're going to look at what happens. We're going to look at this, and then we're going to look at this here. And we're going to split this reaction into 2 parts, and that's called a half reaction. We're going to split it into a copper part and a silver part. Okay, so what we do is we just write the copper part and then the silver part, but we're not done. Okay, so if you look back at the previous slide, you'll see I could just take the copper out, it looks like this, and then the silver looks like this. But what we're missing here is we're missing this. It's a 2 plus. That means it lost, I mean, you know, plus, when something becomes plus, that means it loses electrons. So this guy, so we need to say that electrons have been lost from this guy. And the same thing, but the opposite here, we see that the silver goes from being plus to having no plus. That means it must have gained electrons. So what we have to do is add electrons into both these equations to make up for the plus here. Okay, so copper goes from Cu to 2 plus, so it's sort of gained a 2 plus, which means it's really lost 2 electrons. Okay, while on the silver, on the other hand, has gained 2 pluses, 2 plus. So that means it's gained, so it's lost, lost 2 plus. The 2 plus is different, okay? It's not 2 plus, it's 2 pluses, okay? So that means it's gained 2 electrons. And so what we have is the copper has lost 2 electrons. They've come off. So the copper has lost electrons. They've come off. So now the copper is 2 plus. On the other hand, the silver has gained 2 electrons. And now comes Ag0. So what happens here is the copper gives the electrons to the silver. Okay, and then we can just add those 2 equations, put them together, and these are called the half reactions. Excuse me, my cat's making noises here. Okay, so this is a half reaction, and it tells us that copper's lost electrons and it's oxidized, and the silver has gained electrons and it's reduced. So one thing you should notice is if you take, if you add those 2 equations together, you get this. So this is the silver part, and so it goes silver here. So when you add the 2 half reactions together, what happens? The electrons cancel out, and you end up with a net ionic equation. So that's a good way to kind of check your half reactions. So putting it all together, this is what you need to do. So let's say I say you have copper, give you the word equation. Now you have some copper, solid copper, and I want to add it to silver nitrate. You would see if the reaction takes place, okay, and if it does, you would write out the word equation. All right, and then what you would do is you write out the chemical equation, okay, the balanced chemical equation, and then write the ionic equation, show what happens in water. Okay, and then you lose your spectator ion, you end up with your net ion equation, and then you have your half reactions, okay, and tell what's happening here. Okay, so your goal will be given 2 reactants names. First of all, you're going to have to determine if the reaction takes place. Okay, by using the activity series. And if it does, then you write the following. You write the complete word equation with its states. The balanced equation, net ionic equation, the half reaction. Tell me what's being oxidized and reduced, and also tell me the spectator ion. And we're going to go over some examples here. So let's start out with this one: solid lead added to aqueous lithium chloride. Well, we have to see if the reaction takes place, so we go to the activity series. Okay, so if the reaction takes place, lead would have to be higher on the periodic table than the lithium. Okay, and you look at if you go back in the activity series and you see that this is not the case, this is not higher, lead is not higher, so this reaction will not take place. So if you get a situation like this, you don't need to do the rest of the steps. Okay, so let's do one that does work. So let's say solid potassium plus aqueous iron 3 sulfate. Will this reaction take place? Well, potassium, if you look at activity series, it's higher up than iron, so yes, the reaction take place. Right, so first of all you have to write is the word equation. So solid potassium plus aqueous iron 3 sulfate will yield solid iron plus aqueous potassium sulfate. Okay, notice you just swap the names. So the potassium takes place of the iron and the iron comes out. Okay. Right, now what you want to do is I'll write the equation. The way that I do it is I write the unbalanced equation. I just write out the chemical formulas of each. So solid potassium, when it's a solid, okay, and not an ionic compound, it gets a 0 charge. All right. Iron 3 sulfate, so this is from the material from what we covered in the last set of tests, quizzes. You get, this is the chemical formula, and then iron, now it doesn't have a charge, and potassium sulfate. Okay, now I want a balanced equation. And again, if you listen to the first lecture on single replacements, you would see that I usually start out with, where do I want to start here? I start with the sulfate, okay? I usually start out with the negative ion and balance it. So I need 3 of them, so I put a 3 here. Okay, so that's my first step. And then I notice I have 6 potassiums, so I put a 2 here. And then finally I fix my irons. I have 2 here, so I do 3 here. Okay. All right. I know some of you probably balanced equations before. You can do it your own way, I guess. But just, it's got to be right. So count them. Make sure they're all counted. Don't split apart your polyatomics. Okay. So this 3 means there's 3. So this distributes, so there's 3 sulfates here and 6 potassiums. Okay, so that's the balanced equation. All right, next thing. Okay, so is the ionic equation. So the next thing that's going to happen is, what does this look like in water? Well, this guy here is going to split apart, and this is going to split apart as well. So this is, you have 2 Fe's, and 3 sulfates. Okay, and when you put them in the water, they all split apart. So you end up with 2 Fe's and 3 sulfates. All right, now this guy over here, we're just going to look at 1 K2SO4. So you have, there's 2 Ks for every SO4, okay, and you have 3 of them, okay. So the number of Ks you have is 1, 2, 3, 4, 5, 6, so the 6K plus, don't forget the plus there, just like over here, don't forget the 3 plus and 2 minus. And then you would have 1, 2, 3 sulfates. Okay, so let's see what it looks on that page. All right, and again, I show you how to do that. So the sulfate, this iron sulfate splits into 2 of these and 3 of these. The potassium sulfate, each potassium sulfate splits into 1 of these, and it does that 3 times. So there's 1, 2, 3, 4, 5, 6 potassiums, 3 sulfates, 3 sulfates over here and 2 irons. Okay, so this is the ionic equation. Okay, if you don't get it, go over it a few times. See how it is. Okay, see how it works. Okay. Right, the net ionic equation is going to get rid of the spectator. What's the same on both sides? It's a sulfate. By the way, for metal, single replacement reactions, it's always going to be the anion that's the spectator. And so this is your net ionic equation. I left off the states here, aqueous and aqueous. Sometimes I forget to do that, but you should be aware of that. Okay, what's next? The half reactions. So what I do is I split the two metal reactions. So I have 6 K zeros going to 6 K pluses, and I have 2 Fe3 pluses going to 2 F zeros. Okay, so now what I need to do is include electrons into both of these. So this guy goes from having no charge to having 6 pluses. That means it lost 6 electrons. Okay, so that's right here. And this guy is lost 3 pluses each 2 times. So that means it's gained 6 electrons. Okay. One side there will always be electrons, and it'll be another metal will lose electrons. So potassium gives off the electrons, so it's oxidized, and iron is reduced. So electrons move from potassium to iron. Okay, so there's 3 different types of single replacement reactions. There's metal with ionic compounds, metal with acids, which we covered in a previous video about single replacements. And there will be another one actually that we didn't cover in the previous set of videos. And I'll get to that in a minute, but I want to go over how to do the full system with instead of have an ionic compound acid. So let's say you have solid aluminum plus aqueous sulfuric acid, and what I'm going to do is that we won't use the activity series for these. Just assume that these are going to work. I only want to use the activity series for the single replacement metals with ionic compounds. So this reaction does take place. So it's a solid aluminum plus sulfuric acid giving hydrogen gas and aluminum sulfate. Now this one may be a little hard to figure out, and I went over it in the previous video. So you could change sulfuric acid to hydrogen sulfate. And then what you can do is just have the aluminum swap places with the hydrogen. And so you end up with aluminum sulfate and hydrogen. So that's how you can figure out the product names, is by, if you change this to its ionic name, that can help you figure out the product. And also it'll help with the chemical formulas. So alumina is Al, no charge. Okay, remember, all by itself. I forgot to put the states in here. So there should be a solid here. This should be aqueous. Okay, AQ. And all right. And so I wrote the sulfuric acid is actually as an ionic compound here. So H plus, and you need 2 of them because you have the sulfate has 2 minus charge. Okay. So, I went over this in the previous video. Okay, and so what happens, you end up with hydrogen and aluminum sulfate. So the balance equation, so I start out with the sulfate. I need 3 of them. So what I do is I put 3 in front of the sulfuric acid. So now I have 3 sulfates. Now I have 6 hydrogens. Okay, so 2 times 3 and 2 times 3. So that's all set. Nothing changed there. And I need to make sure I have the same number of aluminums. Okay, right, there's the balance equation. The ionic equation. Okay, so what happens? So you have this guy, H2SO4. That splits apart in water. So it's H plus. And this was in a previous slide. So you have this guy. So this splits up into 2 H's, H pluses and a SO4 2 minus, and it happens 3 times. So you end up with 6 H pluses and 3 SO4s. Okay, nothing happens to this. Okay, and the aluminum sulfate, well, there's 2 aluminums. And then there's 3 sulfates. I'm not going to write SO4, just S. And so you have 1, 2, 2 aluminums and 3 sulfates. And there's your ionic equation. Okay. All right, the net ionic equation gets rid of the sulfates, and you end up with the things that get oxidized and reduced. Okay, the half reactions, right? The aluminum goes from Al 0 to 3 plus, and it does that twice. So you need to have, so it loses 6 electrons, and H plus, each one gains electron, comes 3 H plus. Common mistake, I just said that before, students sometimes will put a 2 down here. Okay, don't do that. Don't bring the 2 down here. The 2, this splits apart, so it's H plus 2 of them. H plus 2 of them. All right. All right. Non-metal single replacements. Okay, we didn't go over these in the previous slide, but in the first videos about single replacement. But we can also have, instead of metals being replaced, you're going to have nonmetals. So we're going to have a nonmetal, instead of having a metal plus an ionic compound, we're going to take a nonmetal plus an ionic compound. Okay. All right. And the only we're just going to look at nonmetals that are halogens, or the 17th column. Okay. Okay. First thing you have to do is decide if the chemical reaction could take place. So let's say I have these 2 possibilities: fluorine gas plus aqueous sodium chloride. All right, first of all, how do I know it's a gas? Fluorine's a gas. Look at the periodic table, and in the periodic table, usually it indicates by the color of the element. What its state as at room temperature. So what we're doing is assuming all these reactions take place at room temperature and standard pressure. Yeah, 1 atmosphere. Okay. So fluorine gas, and with aqueous sodium chloride, we want to see if that reaction takes place. And then we're going to look at sodium iodine plus aqueous sodium chloride and see if that reaction takes place. So the way that's going to work is you look at the periodic table, and we're just going to deal with the 17th column. So you have F at the top, Cl, what is it? Br and I. Okay. All right. So the lone nonmetal, if the lone nonmetal is higher up, then the reaction is going to take place. So it's sort of like the activities series. It's the higher up the lone guy is, the more the reaction will take place. So if we look here, we can see that fluorine is higher up than chlorine. So we're comparing fluorine to chlorine. We're not looking at the metals here, so non-metals. If fluorine is higher up, then the reaction takes place. And it is. Okay, so this reaction will take place. All right, how about this reaction? Iodine and sodium chloride. Is iodine higher than chloride? No, this reaction won't take place. So we're gonna just take a look at this reaction here. All right, so we're gonna write the word equation. So fluorine gas, aqueous sodium chloride with aqueous sodium fluoride plus chlorine gas. So fluorine is F2. Okay, one thing you'll notice is that this is the elemental form. Okay, metals, when they're elemental form, will just be the single element, like silver is just Ag and so forth. Then we have our diatomics. The diatomics, we'll get this. I forgot the charges here, so this is F2, no charge. Let's do that now, because that's really important. All right. Okay, so fluorine, two of them. I mean, this is diatomic. The whole thing has no charge. So it's F2, no charge. Sodium chloride. Sorry, it's over here. Let's work with the unbalanced first. NaCl, sodium fluoride, Na plus, F minus, and Cl2, no charge. Right, balanced equation. You can either start with the fluorine or the chlorine. I'll say there's two fluorines. So I'll put a 2 here. And now I have I need to put a 2 here. Okay, so this is your balanced equation. The ionic, what does it look like in water? Okay, so you have NaCl. Okay, so NaCl, you put it in water, it splits apart, and then Na and Cl does that twice, so you have two Nas, two Cls. You put the sodium fluoride in the water, it splits apart into Na and F and does that twice. Okay, so there's your ionic equation. All right, the net ionic equation is getting rid of the spectator. In this case, the spectator is the positive ion. Okay, for the metal single replacement, it was the negative ion that was the spectator. All right, so we end up with fluorine plus chlorine. Okay, that's my net ionic, and then what we do is look at the individual parts. We have fluorine going from no charge to 2 minus, so that means it gained 2 electrons. And while the chlorine did the opposite, it went from minus to no charge, so it lost 2 electrons. So the fluorine is reduced and the chlorine is oxidized. Okay, now notice here the lone metal gets reduced and the lone non-metal gets reduced. In the metal single replacement, it was the opposite. The lone metal got oxidized. So in these type of reactions, non-metal single replacement, the lone gets reduced and metal, it gets oxidized. Also, in these reactions, the cation is the spectator. In this metal single replacement, the anion is spectator. So they're opposite of each other. So the non-metals versus the metals single replacement are opposite in terms of what happens. Okay, so the single for non-metals, the lone non-metal gets the lone gets reduced, while in the metal the lone gets oxidized. The spectator in the non-metal is the cation, and the metal is the anion. Now, I don't know if you remember it and don't have to look at it. Remember, memorize, just notice it's a pattern and may help you with it. So that finishes it for a single replacement. Next slideshow will be about double replacement. You'll be given a series of single replacement, double replacement reactions to do, and I'll explain all that at the end of the double replacement video. Okay.